So today, let's begin the section of the course that is concerned with solving not first order ODEs, but second, third, fourth, or fifth, or higher order ODEs. In particular, we will be focused on solving second order differential equations, but some of the work that we introduce, especially in the next few sections, will work with higher order ODEs as well. So by the end of today, let's give some example of some higher order ODEs representing some real-world applications. And then let's do some work practicing determining whether a given function is a solution to a higher order ODE. So recall that an ODE was called second order if it contained a second derivative and no derivatives of higher order. Third order would contain a third derivative and nothing larger than that. Fourth order would contain a fourth derivative and nothing larger than that, and so on and so forth. Now, an initial value problem for a first order differential equation usually only had one data point that was given to us. But for a second order ODE, we usually have two values given to us. For a third order, we usually have three values. For a fourth order, we usually have four data points, and so on and so forth. Now, for an initial value problem, we usually are given information about the original function y and the function constituting the first derivative y prime. For example, what's given below would be an initial value problem. Y double prime minus 3y prime minus 4y equals 0, where we require that initially the value of y is equal to 4, and initially the value of y prime is equal to 1. Now, someone has determined that a solution to this ODE has the general format number times e to the 4x plus number times e to the negative x. Let's figure out, based on this given data, what the values of C1 and C2 would have to be to make this entire initial value problem true, to satisfy not only the differential equation, but the initial conditions. So first, let's make sure that the ODE is satisfied, which will require us, among other things, to determine the value of y prime and y double prime. So if I take the first derivative of this function, I get 4 times c1 e to the 4x minus c2 e to the negative x, and if I do it again, I get 16c1 e to the 4x plus c2 e to the minus x. So if I plug that into our differential equation, here is y double prime, here is y prime, here is y, so negative 4 times the original function, and we need to make sure that when everything is said and done, that this works out to be 0. Now, with a little bit of arithmetic, we find that we have 16c1 e to the 4x plus c2 e to the minus x. We have negative 12c1 e to the 4x plus 3c2 e to the negative x, minus 4c1 e to the 4x minus 4c2 e to the negative x. All of that needs to be equal to 0. But if I start looking at the like terms, I see that I have a positive 16 c1 e to the 4x, negative 12 of the same, and negative 4 of the same. So those combine and become 0. I have a plus c2 plus 3c2 minus 4c2 at e to the minus x. So those also combine and become 0. So the first condition is sort of automatically satisfied. Independent of the values of C1 and C2, the differential equation that I'm given is true no matter what. So to determine the values of these constants, maybe I'll look to the other two requirements, that y of 0 has to be 4 and y prime of 0 has to be 1. So if I plug 0 into the original function y, then y of 0 is going to be equal to c1 plus c2. that's supposed to be equal to 4. Now this single equation has two unknowns, and since I have more unknowns than equations, I'm not able to determine the values of either C1 or C2 just yet. So let me go ahead and use my second given condition. Y prime, when I plug in 0, has to output 1. So plugging 0 into this function, I'm left with 4C1 minus C2 and that's supposed to be equal to 1. Now I have a system, two equations with two unknowns, and this system can be solved for C1 and C2. If I add these two equations together, canceling out C2 and negative C2, I'm left with 5C1 equals 5, which implies that C1 is equal to 1. And if I substitute that back in, for example, to the first equation, then that tells me that 1 plus C2 must be equal to 4, and therefore C2 must be equal to 3. So if I have these two particular values of these constants, then this equation, y equals C1 e to the 4x plus C2 e to the minus x, represents a function which is a solution not only to this second order differential equation, but to this entire initial value problem. Now in the previous example, we saw that a general solution to a differential equation could be refined to a single specific solution by specifying the value of y at a single position and y prime at that same position. And this was called an initial value problem. But it's also possible to specify a particular solution by requiring the original function y to have particular values at two different locations. Something like this is usually called a boundary value problem. We are requiring y to have specific values at two different locations. For example here, let's determine the values of C1 and C2 so that y equals C1 e to the x plus C2 e to the minus x satisfies the following boundary value problem. The ODE that must be satisfied is that y double prime minus y must be equal to 0. Not only that, but the function must be equal to 0 when we plug 0 in, and must be equal to 1 when we plug 1 in. So now, if I calculate y prime, which is C1 e to the x minus C2 e to the minus x, so I can get y double prime, C1 e to the x, plus C2 e to the minus x. We can see that y double prime has just turned right back around and become the same thing as the original function y. Since y double prime and y are equal, if we subtract the two, y double prime minus y, then that will definitely be equal to 0 as required by our differential equation. So once again, to determine the proper values of C1 and C2, we need to look at these boundary value conditions. We need to make sure that y of 0 is 0 and y of 1 is equal to 1. So let me plug 0 and 1 into the original function. Y of 0 is equal to C1 plus C2, and that has to be equal to 0. The original function y with 1 plugged in is given by C1 times e plus C2 times e to the negative 1, and that's got to be equal to 1. Once again, we have a system of equations with two unknowns, and in this case, I think that the easiest way to solve this particular system might be to use substitution. For example, I can take this first equation and use it to get the statement that C2 must be equal to the opposite of C1. Let me plug that back into the second equation, which now tells me that C1e minus C1 divided by e must be equal to 1. So now I can factor C1 out of the two terms on the left side, which tells me that C1 is equal to 1 divided by e minus e to the negative 1. And then if I remind myself that C2 is the opposite of C1, then that implies that C2 is negative 1 e minus e to the negative 1. So initial value problems and boundary value problems refer to two ways to take a general solution to an ODE which contains some unknown coefficients and refine it so that you know the values of those coefficients and you're looking at a single particular solution. So how do higher order differential equations arise in nature? Well, we have the spring mass systems that we looked at very briefly in video 1. Those were second order. They were second order because they were concerned with the second derivative of the spring's position, its distance from resting state, from equilibrium. The second derivative representing acceleration, which, when multiplied by the mass of the object attached to the spring, represented the force acting on the spring, which was proportional to the spring's distance from equilibrium. Yesterday we looked at circuits that contained only a resistor and a capacitor, or only a resistor and an inductor. But a natural question is, what if the circuit contained all three components? In that case, you can totally still set up a differential equation representing the impressed voltage, the resistance, the inductance, and the capacitance. But this time the differential equation is going to be second order instead of first order. If we take 1 over the capacitance and multiply it by the charge, and if we take the resistance and multiply it by the derivative of charge, which is equal to the current, and if we take the inductance and multiply it by the second derivative of the charge, then the sum total of that is equal to the impressed voltage. It turns out that you can also use higher order differential equations to measure how much a beam is bent or deflected underneath a load or a weight. Under normal circumstances, the beam might be straight, but if you put a weight onto the beam bends. So the question becomes, what is the relationship between the amount and the position of the weight on the beam and the bending of the beam? So if I use y to represent the amount by which the beam bends, and I use w to represent the weight on the beam at horizontal position x, the deflection can be represented by a fourth order differential equation. If I take the fourth derivative of y and multiply it by a constant, where this constant represents the rigidity of the beam, the fourth derivative of y multiplied by this constant is equal to the weight or load at the position x. Finally, some simple pendulums can also be represented by second order differential equations. If I want to think about the angle of the pendulum, maybe called theta, at a particular time, then it turns out that the second derivative of theta with respect to time is proportional to the sine of the angle theta, and in particular, the constant of proportionality is related to gravity and to the pendulum's length. Now, we won't be studying all of these examples in detail. We will be returning in particular to the case of RLC circuits, and we will definitely be spending some time on spring mass systems, but you'll probably encounter these other two applications of higher order differential equations later on in your engineering courses. Starting tomorrow, we're going to establish some theorems that help us to construct solutions to differential equations of higher orders. And once we have those theorems down pat, we're going to introduce some actual concrete techniques that can be used to solve higher order differential equations.